This is a project I've just finished in the workshop. This is Rubidium frequency standard. Basically gives you a very accurate 10 megahertz reference. It's an atomic clock basically. The rubidium is boiled off in a chamber, and this is detected by a photocell that's fed through what they call a physics unit. This basically detects the rate of the boil off. I don't understand exactly how it works, but it's something to do with the way the molecules boil off. When they reach boiling point, they've got a sort of a resonant frequency. The way I suppose they collide inside a little glass tube, and this is picked up by a photocell that's connected to a oven-controlled crystal oscillator. There's a lot of information. I'm not very good at explaining stuff like this, but there's a lot of information on YouTube about these oven-controlled crystal oscillators, and of course the rubidium circuit as well, and how they work. Now, these used to be available fairly cheaply on eBay, but now they've become quite expensive to buy second-hand. Most of them come from China, and they're ripped out of old, apparently, old cell towers, the old GPRS towers and all that sort of thing. And probably the old-fashioned towers, where they needed a very accurate frequency standard, but all the stuff's been decommissioned because obviously the technology's moved on with 3G and 4G. So I bought this one second hand from a seller in the UK. Now you'd expect to pay £130, £140. I actually get this one a bit less than that. And this is basically what it is. Basically, it's just this box here. I've mounted this inside an external hard drive case. I'll come to that in a minute. You've got various inputs you need to connect up. So there's various different types here, and you have to be a little bit careful to make sure, even though they've got the same part number, FE-5680A, there are different varieties of this, and they're all very slightly different. Now, this one here has a 15 volt supply, and also a 5 volt supply. The 15 volts to 18 volts is actually, it will work on 15 to 18 volts, and basically that does the bits for the rubidium boiling, and I think all the heater for the oven and things like that, whereas the 5 volt does all the electronics inside for the detection. So it's two separate circuits. Some of them have an RS-232 port for allowing you to manipulate the frequency. This one's 10 megahertz, and the majority of them are 10 megahertz, but some of them are adjustable for other frequencies, whatever you want, I think, more or less within range, within reason. This one, pin output here, pin 3, is a byte output, built-in test equipment, which is basically a logic. It's logic low when it's good, which basically means that the oscillator's in lock and it's up to frequency. Now, what I've done there is I've dropped it through a dropping resistor, and it goes to an LED on the front panel. That's fairly straightforward to do. So when it's cold, I've got a light that comes on the front panel to show that the unit's actually out of lock, or it's not up to temperature. What you can do is you can wire that in conjunction with the 5 volts, and just turn the diode around the other way, the LED around the other way, and it will actually give you a byte high. So when it's actually in lock, the light will come on. But I decided to do it with the blue LED. Looked nice, so I decided to go with the blue LED. And you can see here in the bottom here, it's all been glued in. I've bolted this as a TO220 18 volt regulator. So basically it allows me to run with a 19 volt supply, or even a bit higher, with no problem at all. That's an old computer power supply with a different lead put on the end of it, as you can see there. And then the 5 volt, there's a 5 volt regulator here. Now this was a bit more of a problem because I've had to drop from 18 volts to 5 volts. Well, dissipation was a bit of a problem with the regulator getting hot. So it's got this 2 watt power resistor, 100 ohms in series, just to bring the header volts down a bit, so it doesn't dissipate so much in the regulator itself. So that's what that is down there, and it's all glued in with Celastic, so it's all sort of pretty solid. I mean, it doesn't look very pretty, but it's pretty solid and it's reliable. Because the case is negative, the regulators can be bolted straight to the chassis, because it's all at 0 volts anyway, so that's no need for insulators or anything like that. Now the total power supply of this unit is probably around, I think, about 1.2 amps, 1.3 amps on startup, probably a bit higher than that actually, as the oven controlled oscillator warms up, and it's also the rubidium starts to heat the oven in the rubidium standard. So it takes a little while for it to for the current to drop back, but once it drops back, it's down to about half an amp, which is not bad. Now they do run hot. I don't know if you can see there, but it's mounted on a aluminium sheet, and that in turn is mounted to this old iAmega hard drive case. Now this case was absolutely perfect for this, because there's a couple of hard drives that were being thrown out. They're old RDE 60 gig hard drives that they were throwing out, so I saved the case with the idea of making something out of the cases, because the cases were this nice extrusion aluminium. You can see it's in the iAmega stickers on the back. Now I haven't really finalised the back connection of how to connect it up, but I've got this flying lead for the supply to it, and at the moment it's just coming through this hole here. I'd like to make something a bit better than that, but it's functional at the moment, and that feeds up to the front end here, where all the regulation's done. And we've got reverse polarity protection as well with these regulators, so that's good. And you've got quite a wide range of voltages you can use, so anything from really 15 volts probably up to about 23, 24 volts would probably be fine before you start to run into dissipation problems again with the regulators. Now the front panel, we've got a nice label printer at work. We've had some labels made up for it, so that looks really quite nice and professional. The only thing that does let it down is this old BNC mounted on the front. Now I could have used an SMA connector, I suppose, at the front, but the nice thing about a BNC connector is it's you know, you've always got a BNC adapter, so it's nice to sort of use this BNC connection. You're not hunting around for sort of adapting different parts and different bits and pieces. So let me just let's just power it up, and I'll show you what it does. Okay, you see the power is on now, and we've got the looks quite nice, the red LED on showing the power, and the blue showing that the well, basically it's not up to temperature yet. It's not hasn't locked, the rubidium hasn't started to boil, and the rubidium boils quite at a low temperature. It's about 35-40 degrees Celsius from memory. Need to check that, but it's a low temperature, so it doesn't take long for it to sort of get working, whereas an oven controlled crystal oscillator will probably take a while to lock, usually sort of 5 to 10 minutes. This usually locks within a couple of minutes, though it's fairly cold in the workshop. We'll see how long it takes to lock. Now what it's doing at the moment is it's sweeping up and down the frequencies to try and find the point where it will lock. Now if you look at this on the signal generator, the frequency counter, you'll see here, if I catch up the right thing, no, that's not a good idea. Let's click my leads up correctly so we could. It's searching up and down the frequency, waiting for a lock. So basically, it starts at the low end, starts sweeping upwards, and starts to look see if it can get a lock. And what you'll notice is it will stay here for a while, and then it will start to sweep again, and then eventually, once it's warmed up, it should. Here it goes. It's sweeping up now. It didn't get a lock, so it will just keep going round until it gets a lock. And as I say, it usually takes a couple of minutes to do that. Now the big advantage with something like this is it's accurate to sort of like about 1 millihertz. So you know, at 10 megs it's extremely accurate, more accurate than an oven controlled crystal oscillator, and it's stable. You know, it will stay at this frequency for sort of like more or less indefinitely, really. Especially this one's quite well aged. They drift sort of a few millihertz, a few hertz, well no, not even a few hertz, a few millihertz maximum. They really are very, very stable. And the next best thing to a cesium clock, really. So it's just waiting for it to come into lock now. It's still searching through. It takes a little while usually when it's cool, but it's shouldn't be much more than a minute now, I shouldn't think, and then we should get the lock light go out. As you can see at the moment, it says it's unlocked, and it's just doing its thing. I can't measure the power obviously because I'm running on an external supply, but at the moment it'll be down to about an amp, I should think. So it's not horrendous, but you do need a fairly spunky power supply to keep the thing running, and that's why I'm using a laptop power supply that I think it delivers about 3.5 amps, so shouldn't be any problem at all. It's not even any sign of it warming up really yet, but I can feel a bit of heat from the front where the regulators are obviously working fairly hard. Just give it a bit more time. And it seems to me that, you know, it really is quite dependent. Obviously the workshop has got down to sort of about 3 degrees overnight, so this thing will take a little bit of time to get going. But let's just sit back and wait for it to lock. Okay, we have lock. Light's gone out. That means the rubidium has boiled, and it's detected that, and it's basically disciplined the oven control crystal oscillator to run at the right frequency. And you can see there, let's get maximum resolution out of the meter. Now the breaker's been on for about half an hour, so that probably hasn't quite fully established its full lock, but you can see how stable that is. And you'll probably find it will just drift about a bit for a while, and then usually you'll find within, well, a minute after a lock, it's absolutely rock steady. So let's just show you what it looks like with the case back on, and you can leave some comments maybe and see what you think. Okay, that's it back in its case. I've already had to turn the power off again whilst I was putting the back on, so it will take another few minutes to lock. There you go, it's locked straight away now because obviously it's up to temperature. But it's a nice. The case is lovely. It's a nice solid aluminium case, and it's always worth saving these hard drive cases because they're just the right size for quite a lot of projects. And this one particularly fits in here perfectly. And it's still got enough ventilation, and because it's aluminium, it will sink away quite a lot of the heat because these will run quite hot, and it is best to try and keep them as cool as possible. But yeah, that's the Rubidium frequency standard, and thanks for watching.